In this topic, we're going to look at critical path analysis, which is a way of making projects more efficient. We're going to look at how to draw a network from a precedence table of activities. We're also going to perform an algorithm called a forwards pass and a reverse pass in order to calculate the earliest time that an activity can start and the latest time that an activity can finish. So the ideas in critical path analysis are used to make projects more efficient. This can be by reducing the overall amount of time that a project takes if it has a number of different activities, or it can be used to reduce the number of people that need to work on the project at any time. It's been applied in real-life situations such as healthcare to reduce the overall waiting time for patients. And it's also used in various different types of project management where the idea is to make projects as efficient as possible. So we're going to start by considering the project of building and selling a house. So these activities need to take place before the house can be sold. Some activities can be done at the same time, and some activities depend on other activities being finished before they can start. So we're going to put these in the order that they can be done. So the first activity will be to lay the foundations of the house. Once this has been done, the walls can then be built, so we're going to put that after the foundations. And after the walls have been built, the roof can then be put on. We can also put in the windows, that can happen at the same time. Once the roof has been put on and the windows have been put in, the walls can then be plastered. The kitchen can then also be fitted at the same time. And once those things have happened, the house can be decorated. The house can be advertised and sold alongside all of this going on, as the house doesn't need to be completed in order to be advertised. And the lawn can be laid any time after the walls have started to be built. The buyers moving in depends on all of the other activities being completed, so that is going to be the final activity coming after decorating the house, advertising and laying the lawn. So this can be shown as a network. So we just replace all of the activities with letters and use edges to show when an activity comes after another activity. Another way of showing the same information is in a precedence table where we show activities and which activities need to come after others. So if we were to label the activities here, we only put the immediate predecessor on, so we don't need to put every activity that has to have taken place before that one, just the one directly before it. So activities A and B don't have any immediate predecessors because they can happen as soon as the project starts. Activity C has one immediate predecessor. You can see on the diagram that there is one activity to the left of C, and that is A. So we put A as its immediate predecessor. We can see that D has one immediate predecessor again, C. We can see that E and F also have that same immediate predecessor, C. When you look at activity G, G has two predecessors. G depends on D and E both being completed. So D and E go in the precedence table as the immediate predecessor. H has an immediate predecessor of activity D. I also has two immediate predecessors, G and H. And then J is the final activity. Any activity that doesn't have anything after it is then put in as the immediate predecessor to J. So in this case, we've got B, F, and I are all the immediate predecessors to J. That way we've got just one final finish point. Sometimes you will see that there will be an additional activity called the end, where everything leads into to show that the project has been finished. This isn't necessary, so as we can see here, J also doubles up as being the end activity. So the precedence table doesn't usually have the names of the activities in. It does usually have the duration of each activity. So the length of time it takes, this can be in hours or days, as long as it's consistent. So the duration for each of these activities is shown here. So we're going to put the information from the precedence table into a network, and on each node, rather than just put in the activity name, we are going to put some information about each activity. So each node becomes a box which is cut first of all horizontally, so that we can put the name of the activity at the top, in this case just A, B, C, but then the bottom half of the box is cut into 3. The reason for that is so that we can put 3 pieces of information in. So the activity name goes at the top, and then in the middle we put the duration of each activity. So that can be copied from the precedence table. So we can put the activities there. The first box is then the earliest time that an activity can start in order for its previous activities to have been completed. And in order to find these earliest possible start times, we need to perform a forwards pass through the network. So the way a forwards pass works is that we start with any activities that don't have any immediate predecessors. In this case, we're going to start with activities A and B. Because they have no immediate predecessors, they can start immediately. So they both have an earliest start time of 0. We then need to work through the network and consider any activities where all of their predecessors, all of their previous activities already have an earliest start time completed. So in this case, we're going to start with activity C, because C depends on A, and A already has a start time of 0. And we consider that if A starts at 0 and has a duration of 4, then the earliest start time for C will be once A is finished. So the earliest start time for C is 4. We then work through again, only considering activities where all of their predecessors have got an earliest start time. So we can now look at D. D depends on C. If C has an earliest possible start time of 4 and a duration of 3, then the earliest possible start time for D will be 4 plus 3, which is 7. You can see that we've also got the same there for E and F, because they also depend on C only. So E and F also have 7 as their earliest start time. It gets a little bit more complicated when an activity has 2 or more immediate predecessors. So for example, activity G depends on both D and E being completed. So in this case, we need to consider the sum of the predecessors' early start time plus the durations, and then take the largest of the 2 so that we can ensure that both activities have been completed. So for D, we've got 7 plus 2 is 9. For E, we've got 7 plus 1 is 8. So the earliest start time for G, so that D and E have both been completed, would be 9. I'm then going to continue in this way. So we can see that H depends on D only. So 7 plus 2 for D gives us an early start time of 9 for H. Then we consider activity I. So activity I, we need to consider its 2 predecessors. G, if we do 9 plus 1, we get 10 for G. And if we do 9 plus 3 for H, we get 12. So the largest of those 2 is 12. So in order for I to start, we need it to have an earliest possible start time of 12 in order for H to have finished. Finally then, activity J depends on 3 activities, I, F and B. So we're going to find the largest sum. For B, that will be 0 plus 8. For F, it will be 7 plus 2. And for I, it will be 12 plus 2. So the largest of those is 12 plus 2, which is 14. We've now completed the forwards pass. So that means that every activity now has an earliest possible start time. That doesn't mean that it's definitely going to start at that time. It just means that as long as nothing else is held up earlier in the chain, that is the earliest time it could potentially start. We're now going to perform a reverse pass to find the latest possible finish time. Sometimes this is known as a backwards pass. So if we look at J, we can see activity J starts, the earliest possible start time is 14, its duration is 1, which means that potentially J could have finished by 15. Sometimes you will see an activity called end, which shows the end of the full project. End would have a duration of 0, which means that you would give it the same early time as late time. In this case, we haven't got an end activity, we're just using J So we're doing 14 add 1 is 15. We're now going to work in reverse, backwards through the network, this time taking the latest possible finish time of an activity, subtracting its duration, and then that will give us the latest possible finish time of the activity before it. If there's more than one option this time, so if an activity has more than one activity after it, then you need to take the smallest of those two to ensure that nothing gets held up. So in this case, for J, we're going to do 15 take away 1. That gives us a latest possible finish time of 14 for activity I. Then going to look at G. So G is 12 because the immediate successor of G is I. 14 take away 2 is 12. Similarly, H only has one activity succeeding it, which is I. If we do 14 take away 2 from I, we also get 12 as our latest finish time for H. If we now look at activity D, we can see that activity D has two activities after it. It has G and H. If we do the subtraction for G, we get 12 take away 1 is 11, and for H we get 12 take away 3, which is 9. In this case, we have to take the smallest of those in order to ensure that there are no hold-ups. So the smallest of those is 9. E only has one activity after it. So 12 take away 1 from G gives us 11 for the late time of E. F again only has one activity after it, that is J. So if we do 15 take away 1, we get 14 for our latest finish time for F. Activity C now has 3 possible activities after it, so we're going to do 9 take away 2 for D, 11 take away 1 for E, 14 take away 2 for F. Choose the smallest of those 3 options. That gives us 7, that's the 9 take away 2 from D. So the latest possible finish time for activity C is 7. Just to finish off then, activity A has a latest finish time of 4, that comes from activity C, 7 take away 3. And finally, activity B has the latest possible finish time of 14. That comes from doing 15 take away 1 from J. So we've now performed a reverse pass or a backwards pass through the network to find the latest possible finish time for each activity in the network. Now please complete exercise 4.1 on page 60.